In this project, I will demonstrate how to use clock generation circuit in FPB RA0E1 board. Open ESK Studio, then click on this file icon, then select New, then select NSS C++, then select NSS RA project. A new dialog box will appear. You can give name to your project here. After naming your project, click on this next button. From this drop-down menu, select FPB RA0E1 board, then click on next button. For Smart Bundle selection, we can select None option. Here we can select Executable and No Autos option, then click on Next button. Here select Bare Metal Minimal, then click on Finish button. Now click on Open Perspective button. IDE will open FSP configuration file. In FSP configuration file, click on Stack tab, then click on New Stack, then click on System, then select Clock Generation Stack. Now click on Clock Generation Stack, then click on Properties window. In Properties window, you can find basic setting and pinout related to Clock Generation Stack. Initial clock source for different peripheral and timer are defined in Clock tab. If you open clock tab here, you can observe different divider and setting related to source clock. These settings will be initialized at bootloader stage. Now click on Stack tab, then click on this information icon to open FSP documentation. Initial clock settings are defined in Clock tab. These settings are initialized during startup process before the main function get called. If you scroll down further, you can find a basic example how to change system clock from high speed on chip oscillator to low speed on chip oscillator. After changing system clock from high speed to low speed, then we will measure the power difference between these modes. Now click on generate project content, then click on proceed button. Now expand src folder, then open hallentry.c file. First, I will define FSP error variable in hallentry function. Now in project explorer tab, expand clock generation stack, then drag and drop clock generation circuit, open function call in hallentry.c file. Now use assert function to make sure clock generation circuit open function call was successful. After that, we need to start low speed on chip oscillator clock. For this purpose, we can drag and drop clock start function call from developer assistant tab in hallentry.c file. Now we can use RBSP software delay to wait for low speed on chip oscillator clock to get stabilized. Before changing the system clock, we need to update the divider for peripheral and timer clock. From FSP documentation, I am copying the divider setting to update system clock in FEV RA0E1 board. Now I am defining while one loop here. In while one loop, we will check the user switch. If user switch is pressed, then we will update the system clock. Now expand developer system tab, then expand GPIO stack. From GPIO stack, drag and drop GPIO pin read function call in hallentry.c file. Now define BSP IO level variable. Then in pin read function call in last argument we need to provide its address, and for second argument we can use SW. This was the pin name given in FSP configuration file. Now we can use if condition to check whether the user switch was pressed or not. If user switch was pressed, then we can update the system clock. Now expand developer assistant tab, then expand clock generation circuit stack. From clock generation circuit stack, drag and drop system clock set function call in hallentry.c file. For second argument, we can use CGC clock loco option. Now for the last argument, we need to provide the address of divider variable. Now use assert function to make sure system clock set function call was successful. Now I will present a short recap for the project source code. First we need to call clock generation circuit open function call. After that we need to start the source clock which we want to set as system clock. Then we need to wait for its stabilization period. After updating the driver, we need to call system clock set function call. Now click on your project name, then click on this hammer icon to build your project. After build is complete, right click on your project name, then select debug as, then select NSS GDB hardware debugging. Now click on switch button to open debug perspective. In debug perspective, click on resume button twice. Now click on terminate button as we want to measure the power difference between two modes. We need to terminate the debug session. After debug session is terminated, click on reset button. Now application will run in high speed mode and consume 2.5 milliampere current. Now click on user switch. System clock will be changed to low speed clock. After that, power consumption will become 0.3 milliampere. That is almost 6 times reduction in power consumption.